It's a great honor to be invited to speak in this very special consortium, and I'd just like to start with connecting a few milestones that relate directly to the challenges and advantages of this particular method that I will elaborate on in a bit here. Obviously, you're looking at the very first non-contact, non-imaging mapping system developed by Waller and Eindhoven back at the turn of the last century. And as we carry on, there we go. We also have the advent of invasive electrophysiology when the first intracardiac electrogram was recorded in 1945. The so-called founding of modern EP mapping when the accessory pathway potential was ablated. And then many advances have been made over these more than 100 years. However, none had evolved the methodology beyond voltage-based electrographic imaging until the introduction of the charge-based methodology. So if we look at, in parallel with that very high-level overview, look at some technological milestones. We have the analog chart paper recording systems that came into use since the 1940s, computerized tutor recording that came in the late 1980s, and then more relevant to what we're talking about today, obviously, computerized 3D mapping from the early 1990s with the Cardo system, the Insight system in the early 90s, Arrhythmia Orion mapping system, and the Cardio Insight ECGI body surface mapping system in the mid-2000s. And then starting in 2011, the Acutus charge density-based AcuMap mapping system. If we look what happened over that entire 100 years at very specific intervals, we can also connect some dots on the rich history of knowledge that was required as the basis for all of this work. Back in 1932, I see we have something in the way up here. Hopefully everyone can see that. The work of Frederick Wilson and others, Thomas Lewis, William Crabb and others, where the notion that there was some sort of a double layer generated in some way could be analytically calculated in 3D space using analytic geometry. Obviously, from 1938 to 1952, during that whole period of time, this work was elaborated into the Hodgkin-Huxley model of the action potential. We have Geselawicz's important and famous work in 1967 on the notion, the quantitative notion of an inhomogeneous volume conductor and the potentials therein, the bidomain model that followed that, the intracavitary non-contact probe for detecting sites of origin that was done by the Milan group with Bruno Taccardi and his group. This particular work was what inspired me to get involved in inverse cardiology. And then other aspects that in parallel were required to get to the point of being able to image these electrographic notions. Ostendorp's and von Oosterom's work on interpolating on a triangulated 3D surface. The rich history of the entire career of Professor Planzi and Barr, and leading to important texts on the whole quantitative approach to bioelectricity. And then coming closer to what we need to talk about today, a practical implementation using boundary elements by Durar-Khoury under the leadership of the CVRTI team and Professor Yoram Rudy with his group from Case Western and the Utah CVRTI. This was very foundational work that paralleled the work at Endocardial Solutions and in fact served as an independent corroboration of the basis for the work. Finally, if we then look at the work in 2004 that was published by Charu and Raja and Ping and Paul, under Yoram Rudy's guidance, again, the non-invasive electrocardiographic imaging for electrophysiology and arrhythmia, which now, of course, has been brought in to Medtronic's work. So finally, if we look at the work that has been performed by Professor Gunther Scharf from 2006 to 2010, when this work was self-published in the physics forums, and we have the charge density-based source model of the cardiac electric field. It is actually with great sadness that I have to report that Gunther Scharf has passed away. Last month, I was really hoping that he would be involved in some discussion in this very forum. And in fact, we've, as we all know, we've lost a number of our mentors who have contributed so much to the field that we work in. But what I would like to do is describe in his own words an evolution from the ohmic biodomain model introduced by Miller and Geselowitz, which is a source model based on current density proportional to the transmembrane potential and which encompasses the whole torsal volume. And Professor Scharf recognized that the assumption of a membrane current permeating the extracellular space may hold at the level of cellular dimensions and smaller. He was a little bit worried, being the theoretical physicist that he was, coming completely unindoctrinated from the entire history that we've all witnessed ourselves in the academic work and in industry. He worried that the assumption and hypothesized that the assumption may not hold at the level of tissue dimensions and larger, when the highly dissipative nature of the entire torsal volume conductor is considered. So Professor Scharf tested this hypothesis by developing a direct macroscopic derivation of the cardiac potential field from first principles of Maxwell's equations. And this culminated in what you might think of as a more capacitive charge-based formula that is a solution to Poisson's equation. And this is a source model based on polarization charge density, the Helmholtz double layer, in the extracellular domain adjacent to active ion channels that does not require a prerequisite assumption on the source, especially in terms of, let's say, a current source. One of the ways that I've sort of thought about this myself is noting that there could be a kind of an analogy in circuit systems, circuit network theory, where we have a Thevenin equivalent source and we have a Norton equivalent source. And there could be some way of looking at this as a current density versus a charge density. So some of the challenges that we have all well known together in all of the work that we've done to approach electrographic image resolution that approaches 1 to 2 millimeters, which is the clinical requirement. And this now fits right in with the previous discussions that have been made about errors in localization and errors in the level of resolution that can be achieved. So we must have a source impedance of the electrodes that is very low. It turns out that the source impedance affects the acquired signal bandwidth. And the best way to point that out is the source impedance of the electrode forms a divider with the input impedance of the amplifier. And if for whatever reasons, the input impedance is compromised to some degree by parallel capacitance and various other aspects of design constraints. And if the source impedance of the electrode is high enough, that voltage divider can actually act as a high-pass filter cutoff value that can actually dominate over the electronic filters that are designed into the system. Signal filters must be distortion-free. It turns out that the industry standard high-pass filters that are used in the conventional systems today distort low frequencies with what you could call exponential deflection tilts and long ramps in the baseline. Amplifier gain error and offset must be precisely corrected, and a lack of correction results in artificial spatial voltage gradients across amplifier channels that are then applied into the inverse algorithm, and they show up in the solution. Data must be acquired from amplifier channels simultaneously, of course, for the global solution. This is the one thing that's easy to do. All of the other ones are where the real challenges lie. Endocardial and or epicardial surface reconstruction must be millimeter accurate if we're going to be directly navigating and guiding ablation. Ideally comparable to the accuracy, let's say, of the segmented CT meshes. Electrode localization accuracy and temporal tracking must also be millimeter accurate if we're going to meet all of these requirements of localizing and navigating and directing treatment. Deploy enough electrodes to meet the spatial Nyquist criterion for all wavefront conduction patterns of interest. Another challenge, the ultimate challenge, of course, is validation. And I'm just showing a quick graphic here very quickly to point out we used the chased model to develop transmembrane potentials, calculate transmembrane potentials on highly granular meshes, 100,000 vertices in the meshes, and then taking the gradient of the action potential of the transmembrane potential to then set up a dipole layer. And from there, we would take this as the ground truth, where the zero crossing could be used to establish the actual activation time of the simulation. And then, of course, we could forward that to achieve the surface potentials. And then we could then also forward the charge density to establish the potentials on the electrodes that were inside the cavity. And then that data would then be applied on the inverse algorithm. And then the same thing would happen in here, where the inverse algorithm would reconstruct the dipole density. And from there, we could forward that to surface potentials. And we could also find the downstroke zero crossing to get the activation time. And the ground truth activation times were compared, and the surface potentials were compared with a voltage to voltage comparison as forwarded from the derived, inverse derived charge density. So that's quite a mouthful, and obviously the ultimate challenge. And then that also led into the clinical validation, where actual contact measurements would be measured, and the forwarded voltage values would be compared voltage to voltage. So the high resolution, if I may truncate that to a more general term, electrographic imaging and mapping system called AcuMap, does apply non-contact cavitary sensing. The anatomy is scanned by ultrasound. The charge density-based algorithm that I alluded to at a very high-level summary a moment ago was applied. All measurements are made and calculated on a frame-by-frame basis throughout the recording time for global mapping. The methodology can be calculated very rapidly on today's resources in computing. So fast remapping is very available, is doable and available to manage multiple morphologies, and then also to be able to assess the effect of ablation. So this is just a quick look at the AcuMap catheter itself when deployed with a 25 millimeter diameter, 10 French shaft. There's a polymeric, conductive polymeric coating that is essentially electroplated onto flex circuits in order to achieve a very low impedance, and from that a high fidelity electrode. We put in a tremendous amount of effort into getting to a very low impedance electrode that lowers the noise and also moves that parasitic high pass corner frequency well down below where we need to be looking for unipolar morphology in the electrogram data. 48 also, ultrasound transducers are also applied. The ultrasound acts as sonar pulses in M mode, not in the B mode pie-shaped image. And post-processing of the surface data completes the reconstruction. And using the impedance-based methodology for localizing and tracking the electrodes, these little squares, white squares, are the actual sensed positions, and the green vectors are the distance measurements made by the ultrasound crystals. So we have to combine the distance measurement, which doesn't know where it's pointing, with the a priori knowledge of how those transducers are fitted and sitting next to or in between all of the sensed electrodes. So that information is combined to achieve the ability to scan using ultrasound.
Dr. B, sorry to interrupt, but time is running out. So could you please wrap up?
Okay, yep, no problem. So the image of the posterior wall of the left atrium is generated in this image. We have achieved a very high signal quality. These are actually non-contact potentials in the left atrium, showing in sinus rhythm the QS and RS and R wave morphologies that are expected and nearly rivaling what we would see with contact. The localization accuracy is applied by using singular value decomposition, which allows us to achieve an XYZ uncertainty inside the beating heart, including respiration compensation algorithm on the order of 1 millimeter. And when we apply that, we are able to see the conduction patterns that have been mentioned in the previous presentations, focal patterns, rotational patterns, which typically are leading circle reentry around high density zones of fibrosis, which tend to not last very long, just a few cycles thereof. And then these multi-directional localized pivoting reentrant patterns called the localized irregular activation. The final thing that I would like to show is this example of all three of these conduction patterns, which speaks to a point that was made in an earlier presentation. Do we see all of these things? And we do in these zones of high density fibrosis, stress points under the years of stretch that have occurred in this etiology of atrial fibrillation. We see this pattern of rotation first, going up the posterior wall, around the Coumadin ridge, back up again. It's faster around the left antrum. It's also going around the right antrum, but it just happens to be faster around the left. But the septal side is catching up. Fusion occurs in the middle, but this does not actually stop the rotation. It just causes it to wobble a bit. We see a long, short morphology and a change in the morphology. And this allows more time for recovery in this particular part of the left atrium, allowing a focus to fire, which is what causes this whole hemisphere now to be refractory, stops the rotation, and then we break down into these patterns of localized pivoting reentry. So the higher resolution that is afforded from going after the charge density, which is a compact electrical entity, we're able to achieve a resolution that's 4 times higher than has been found with voltage-based mapping. And we also see that by processing the signals with adequate temporal sampling and spatial sampling, we're able to identify the conduction pattern on a cycle-by-cycle basis. Thank you very much for your attention.